Welcome everyone. This is computer vision lecture number 11 on pose estimation. Pose estimation is the last of the classical computer vision tasks in this block. Style transfer and image captioning is a little, let's say, off the classical track of tasks in computer vision. So let's have a look at pose estimation. Pose is or means position and orientation, but it comes in a variety of flavors. So for example, in my lab, we track bees, and we do that often only with a position in 2D, that's the center point here, and an orientation. So it actually has three parameters, right? The width and height of those boxes are always constant. So we have a three-dimensional state space. The pose of those weakly electric fish consists of 6 positions of features, of landmarks that we can find on the animal, again in 2D. So the nose, the center body, and then those fin positions. So 6 positions times 2 is 12-dimensional state space. Now, in pose estimation, we can detect the pose of single or multiple objects. Oftentimes, this comes with a slightly different approach of how your network will actually do that and how post-processing steps will look like. Two kinds of approaches are there for you. Top-down means you first get a proposal of this is the object, and then you go deeper and get those feature points. Or bottom up, which is exactly the opposite direction. From a prediction of those feature points, you then merge these up to a skeleton of your fish or your bee or of your toy train. You could also have a prediction of only one possible class, so fish or bees, and if you kind of happen to have both in the same arena, you could then use a multi-class pose estimation algorithm that detects both. Now, pose estimation comes with a couple of challenges. Many challenges are, vision related and are not specific to pose estimation. So, for example, image blur or scale changes, like you can see here, or some of those features will be occluded by other objects or other instances of the objects that we are looking for, or even like here, the hip of the person is occluded by the person's arm. So I think the pose estimation is quite a challenging task, and that's why we love to look at how this can be solved. This is one of my favorite samples, summarizing really what the challenges are here. So that's a sitting person. The hip and the elbow are visible. The ankle or the foot position is behind that lovely cake. Anyway, let's have a look first at data sets, because these are the ones that you'll be working with. A pretty small data set is called Leeds Sports Pose data set. I think it's a little outdated today, but it's, I think, worth looking into it. It only has 2,000 samples and shows only single persons. Yeah, so that also brings the problem or the challenge. What if your network predicts, I don't know, poses or like features of the second person visibly here? You cannot compare this to any ground truth. So another quite large data set with 25,000 images was published by Max Planck Institute. It comes with also 410 classes describing what that pose actually is on an abstract level, right? So hunting or kneeling in church or copying documents are all within these 410 classes. Again, here, this human pose data set only has, or mostly has, single persons. Now, I think the most common data set that people use when it comes to 2D positions of those features is the COCO dataset and its variants. So this has 17, sometimes 18 different parts or like key points, like shoulder or hip or knee, for example. It's the largest dataset available, at least at the time I checked. It has multi-persons, so all the persons in an image are labeled. So that's really cool in terms of performance quantification. If you are interested in three-dimensional poses or 3D reconstruction stuff, for example, you want to look into the human 3.6M dataset linked up here. We will only focus on 2D right now. And before we do that, we have to have a look at evaluation metrics. So for those key points that we want our network to predict, we have positions given in our ground truth, and we compare this to the corresponding prediction. Most of the time, those predictions belong to a certain class, so it will be clear what to compare with the ground truth. And we usually measure the distance, the Euclidean distance, d1 for key point 1, d2 for key point 2. And for the first metric, we look at those limbs, so those body parts or bodies or segments of the skeleton that consist of 2 of these key points. Now, in PCP 0.5, we look at correctly classified or correctly regressed. Actually, it's a regression task, right? Correctly regressed key points for those limbs, and we ask whether the first distance is smaller than half the length between those key points for both of these distances. Yeah, first distance needs to be smaller than half the length, and the second distance too. Now, that may run into a problem if you have short limbs, because then the precision that you want your network to have for those key points is much higher, so it needs to be in a smaller radius around that. And so that's motivating the second evaluation metric called PCK-H 0.5, which looks only at single key points, not those segments anymore. And those key points have to have half the distance from the ground truth of a constant variable or constant property here, which is the head to neck length. Now, these are binary decisions, and then you just count how many, and then you divide by the total number of possible matches, and then you have your percentage. Now, you can also try to assign like a desired precision for each of these individual key points by introducing those key point scales, Ki. And these are numbers that are used in a metric called OKS for object key point similarity, and it's computed like that. So we take e to the minus square of this distance. So again, key point prediction to ground truth distance, but we divide that by a global scale of the object given in a data set, and also times this square of this key point scale. So if you have a large key point scale, for example, here in the hip, this number is larger than, for example, here for the nose, and that makes that number smaller, so e to the minus something smaller is larger, right? So larger distances from the prediction to the actual ground truth are okay in for key points that have a larger scale. So you can think of this like as a tolerance, as a smooth kind of tolerance for that metric. Now then you sum up all these things and you divide by the number of key points, and that's your metric. Okay. Let's start by looking at something that I don't want you to do, which is single object pose estimation, because it kind of shows you how people have been doing it, and which also then creates a problem, and necessitates a solution that we'll then look at, and that will be the focus of our today's lecture. So DPose was a pretty early network that predicted those key point positions by regressing based on the input image to 14 different key points. So that was just a simple network that was used, for single object or single entity pose estimation. So those 14 key points, belong to the same human, or should belong to the same human. Now, this came in two different stages. So first, a network received the entire image, proposed those 14 different positions, and then for those positions, we then put this into a second refiner network that was then used to predict refinement positions, and then you could iterate this a couple of times if you'd like to hopefully converge to the correct key point positions. Now, in multi-object pose estimation, we have a problem that would become huge if you use DPose, right? So look at this. You have the left shoulder appearing twice, the right shoulder appearing twice, the right foot appearing twice, and the left foot as well. So if you regressed to only one set of those features, the network wouldn't know which one to take, or we would hope and pray that it actually assigns the right positions that then make sense and disregards those half occluded or persons here. Right, so we probably won't be seeing an approach with a fixed output here, a fixed regression output to k key points. We need something else, and this is usually being done with the so-called heat maps. So an input image is put in the network, and the network now does not produce a vector of positions, but a map for each of those key point classes, where the, let's say, probability of a certain pixel to be on that key point is encoded. So for example, you have, let's say, green corresponds again to the right shoulder, and blue corresponds to the left shoulder, and red could be the head position or the nose position. Now, we usually represent this how? Exactly, we have a stack of output matrices, right? And each channel in this tensor now represents, the elbow, and the shoulder, and the knee, and all the different types of key points. And then each of these matrices now has width and height of the input image, or some, scaled version of that. So each position in the output corresponds to a position in the input. And now, an output like that would then have to be post-processed to actually get a position, and not many positions. So we would likely post-process this with a local maximum search or a non-maximum suppression. Okay, now let's get to the focus of this lecture. It's called OpenPose. It was published in 2017. OpenPose is really nice because it's open. You can download the source code. You can build yourself. There's a variety of implementations for TensorFlow, for PyTorch, for Caffe. You could also see a broad adoption of this in many applications because it's nicely built and nicely published. So I definitely would propose reading that paper and trying out that code. Oh, and by the way, it's in your assignment anyway, so you have to. Okay, so OpenPose and that paper. Oh, by the way, it's not that paper. It's even a paper before that proposed a solution of this, ambiguity problem, right? So if you have two shoulders and two elbows, how do we match these things together? And the authors proposed a so-called Part-Affinity-Field as an output to the network. And so those Part-Affinity-Fields now encode connections between two parts. So for example, of elbow to wrist or to hand. And the Part-Affinity-Field is a vector field. So it comes with two components, one for X and one for Y for each pixel, right? So if you zoom in on the Part-Affinity-Field for this input, each pixel now has a vector quantity. So X and Y, components for a vector that now points into the direction from the elbow to the wrist. Yeah. So coloring this vector's orientation with different colors from, let's say, red to blue, maybe, you see that arms that go down are like yellowish and that point to the left are greenish. So those affinity fields encode the direction of that limb in the image. Before I show you how this comes all together to then produce skeletons, let's have an overview of the pipeline, let's say, of OpenPose. So an input image is fed into a network that then produces two outputs. One are the so-called part confidence maps. So those are the classical, heat maps for the position of the shoulder or the elbow and all the other, parts. Now, it produces also the previously introduced part affinity fields or paths. And the post-processing of those two kinds of maps lead then to first a matching of those parts, right? So if we have two shoulders and two elbows, the question is, okay, which elbow do we connect that shoulder to? And which elbow is then corresponding to that shoulder? And I'm going to show you how that works. And once we have those connections between two parts, we then merge those parts into skeletons that then make up one human and the other. Now, first, let's have a look at how this network looks like. First, we take a VGG19, and in the lecture, I learned that most of you don't know what VGG19 is. Please have a look in one of those earlier lectures on convolutional neural networks for image classification. VGG19 is a 19-layer deep ConvNet that you can download pre-trained and can use for encoding your image, right? So you put in your you put in your image, and you take the 10th layer, the activations of the 10th layer, as a representation of your image. Yeah, layer 10 is still a convolutional layer, so you still have like location information, and it's not that like downsampled, so it's perfect for that purpose here. Now, with that representation F, we feed that into a network that's called Phi, And it comes with a number t that corresponds to the stage. And the stage now just says, okay, we have this network or this block of layers multiple times, but they do not share weights, so they are different networks, but they all have the same task. They have to create this tensor L, which is the part-affinity field. Let me just write that down for you here. So this, oops, not Laserpointer, Stift. So this one is the part-affinity field. Oops. Now you have a sequence of those blocks, and at each end, at each output of this block, you feed in a loss, which basically compares the prediction to the part-affinity fields of your ground truth, right? So you have to get these beforehand, and then in that sequence of blocks, let's say this is the first block or the first stage, and then you have the second stage, and then what's going on with these spikes there? And then they have the third block. Each time you can get weird spiking here. You can insert your loss. I should write that again. Let me just do that and try again. All right. Right. So you have a block and another block, and you have as many blocks as you want, given by that hyperparameter TP. And that is block number 1. And that is block number TP. Now, F goes in, and at each block, we produce this part-affinity map. And we can use a comparison with the ground truth part-affinity fields to produce a gradient that then helps optimizing each of these blocks. And now the cool thing is the early block B1 gets a gradient of the first loss and of the second loss and of all the other losses or gradients from that losses that happen later in that sequence of losses. Yeah, so that helps against the vanishing gradient problem. Okay, now in the end we have this LT. Oh man, what's happening with my mouse? That wasn't the case when I just had the lecture. So this tensor here, those are the part-affinity fields. And we'll concatenate the output to the image representation, such that this network here, which we can also run in different, in a different number of stages, if TC is larger than 1, to then predict the part confidences. So these are the confidence heat maps. Yeah, confidence heat maps. Something's going on. Anyway, now, so this has 18 key points, but has 2 channels per key point, right? So we have X and Y. So that is 36 channels. I don't know why these spikes occur. Please, I hope you don't mind. So this is 36 channels, times width and height. And that one here has 18, single channels for the parts. So this is 18 times width times height. All right, let's move on and have a look at why do we have those different stages and how do they make the results better. So let's have a look at these images. There are a couple of people in the background overlapping and obstructing. and in that area there are a couple of arms, going on, and the output PAFs of each of these stages is depicted, right? And so what you see is that these part association fields do change, do get better, and that's because each stage, gets the concatenated output of the previous stage plus, with concatenated with the image features F, and so could now learn how to improve things, right? So they don't have to do this all on the image features alone. They can take the previous results and then kind of get better from there. And that can be seen here, and that's why the authors propose doing that. Now the next step, by the way, non-neural, non-network-based computation and task is, how do we know what this shoulder connects to? Is it this elbow or is it that elbow? Yeah. So we have this network here, and we could make this a little simple by saying, okay, obviously a shoulder does not connect to a hand directly. It does so by going through an elbow. So what we first have to do is we start by matching this bipartite graph, right? So we have all the shoulders here, and we have all the elbows here, and we score those links with something that's called PAF scores. So PAF is the part affinity field again, and scores are computed like on the next slide. Right, so we score those connections, and then we do a greedy association of shoulders and elbows, and we do that again with the elbows and the hands, and then we'll merge those matched bipartite graphs into humans. But first, let's have a look at how we do this scoring part. So let's have a look. Let's have a look at this elbow and this wrist. Yeah. And let's say we have two of those wrists. One is here and one is up there. So this is wrist number 2. And now, how do we score this? Well, we first compute a vector that has unit length. We call that V, and we match it to the part affinity field vectors that are on the line between the key point 1 and key point 2, so the elbow and the wrist. So let's say we don't have to, take every pixel, but we can just say we take 4 pixels or 10 pixels or whatever. Let's say we take 4 pixels, exactly those that I've highlighted here. So in the part affinity field, those vectors are supposed to point from the elbow to the wrist. So we expect that the vector V points in similar directions to those vectors given in the flow field, in the part affinity field. So by taking the dot product between V and those Wi's, let's say this is W1, W2, W3, and W4, we take the sum of those dot products, and that is our score. Oh man. Yeah. Okay, so what about a vector V that points to this second candidate and the same flow field here? You will produce dot products that are negative, exactly, right? So because they look into opposite directions. So that score between that elbow and that wrist hypothesis, that score will be negative. Now, let's say you have all the all the shoulders up here, shoulder 1, shoulder 2, shoulder 3, and shoulder 4, and all the elbows. Oh man, all the elbows here. Then we can compute the score between all those positions using the method that I just showed you. Integrating the dot products from the shoulders to the elbows, and then we'll obtain like small values, a little larger values, really large values, maybe negative values. Let's say that's -2, and then we can sort these, from the highest to the lowest score, and so these scores correspond to certain combinations of shoulders and elbows, and now we do this greedy assignment process. So we say, okay, the largest score probably has to be correct, right? So we say the second elbow is connected to the third shoulder, and now these parts have been assigned, so they cannot be assigned in later stages, right? And so up, down here in this list. And but since we haven't yet assigned them, we say, okay, check, cool, yeah. And then for the next score of 3, we see that there are different shoulders and elbows, and then we can assign them to be linked. Now in the third row here, elbow number 1 would be connected to shoulder number 3, but shoulder number 3 already appeared here, yeah. And so we cannot and will not assign these together. And then we can continue and assign parts to belong to each other in this greedy fashion. Now it's greedy, so that means it's not guaranteed to have like a global optimal solution, but for most poses it works, and it's quite fast. Okay, so what we now have to do is to create humans from limbs. Okay, so the first greedy matching produced this link, so that shoulder is connected to that elbow, and the other shoulder is connected to that elbow. And then we did the same matching procedure with this graph, right? So the former link here was discarded, and that former link here was discarded too. Now, since an arm, has usually the same elbow, we can then now connect those subgraphs together when and only if when they share the same part. Yeah? Okay, so this guy connects to this guy, and that guy connects to this guy, and so this is this arm, and that arm here corresponds to these parts. Okay. That was, in a nutshell, OpenPose. I think we should conclude by looking at how this is done, or how you can use this in applications, because I think the variety of those is mind-blowing. So obviously you can read hand poses, read sign languages, communicate with your system, with your computer, with your TV, with your wheelchair, with whatever, to have a channel of communication. And this is fairly stable, so even with cluttered backgrounds, it can be done. And this video is a couple of years ago, so this should work today really, really like a charm. Now, something that we do here in my lab is tracking animals, and then through this be able to have a very rich description of how animals move, of how animals behave individually. So, looking at motion patterns of those fish, for example, or descriptive statistics of how often some patterns appear, and so on. And also describe in a very detailed manner how individuals interact. So how pairs of flies, for example, or bees, or fish, or mice do interactions, right? Or even larger groups, how that works. And this quantitative approach to animal behavior is quite new. It's still growing, I think. It comes with a lot of data and a lot of work, but still people are, seeing new things because of this approach. Now, another really cool application that I found in the web is this. So imagine you are a marketing person and you want to, find a photo in your database of 2 trillion images of a person that does this kind of pose, or is like doing that, or or that, anything. How would you do that? Well, you could like search, in your metadata that you hopefully have in your database, for a description of that pose. But what you can also do is, you run OpenPose on all those trillions of images in a database, and then you can just have a query. So you step on your table and do your pose that you want to find, and then you take that post that's then estimated on your body and search for that in your database, and then you can look up those samples. I like that. And another thing is sports analytics. I think it's a huge thing because sports is huge. So if it's basketball, or soccer in Europe, that's something that people want to optimize. That like those who are doing the sports, but people also appreciate having information about statistics, like the guys that sit in front of the TV. How often somebody throws, from where people throw, how maybe how much that throw pattern change over the course of a game. I don't know. There are many variables that we can extract to learn about, how we move and how we perform. Think of horse races. So horses can be tracked like that, and you can learn about motion patterns. Some, things that you can improve by training the horses, or prevent, if it has like a week or so leg or some muscle soreness, like prevent or detect that soreness and then prevent it from worsening. So the number of applications are just limitless, I think, and we haven't yet seen, I think, what's to come. That's why I think you should be looking at your assignments. You are tasked with looking at failure cases to analyze what's going on in a network. I think the pose estimation task is too big for your consumer grade machines. So that's why we thought of, okay, take this analysis kind of task. So you have to find out why specific examples, don't end up being predicted correctly, what's going on with the network. I mean, that's something that we have to do anyway, right? In developing networks, it's not just collecting data, training network, and done. It's the most work is in finding why the network isn't doing what you want, and interacting with your data, interacting with how inputs are progressively processed and mapped into the outputs, and finding out about how it's how smooth or not smooth is a network. Maybe you have not enough support for some subspaces of your data. Maybe it's overfitting. Maybe it's doing weird stuff, and you have to find out these things. Okay, good. Okay, so that was the one-shot lecture on OpenPose. I hope you enjoyed that. If you have questions, please write me, because you can't ask questions in the Q&A because the Q&A just happened an hour ago. And well, see you all next week. Bye.